Welcome back. Now we'll discuss about two different concepts. One is the antenna noise temperature, and the second is the equivalent noise temperature in two-port devices. Let's see the first one. The antenna noise temperature would be the equivalent noise temperature of the antenna, or the equivalent noise temperature that characterizes the noise picked up and generated by the antenna. This is the noise that the antenna can deliver to a receiver connected to it, right? As I say, these noises might be due to the loss of the antenna, or also by the surrounding environment, right? And there are many possible sources of noise. The most important of them is the noise picked up by sound, but there are other sources as indicated in this slide. In any case, the power or the spectral density of power of all these noise sources can be gathered in a single parameter, which is called the antenna noise, the equivalent antenna noise temperature, right? And there's a definition given by the IEEE which summarizes this concept. Antenna noise temperature is very strongly dependent on frequency, right? Because the various sources of noise are very frequency dependent. At low enough frequency, the main contribution for antenna noise temperature is man-made noise. Then there's a range of frequency going from, say, 100 megahertz to 1 gigahertz, where the dominant contribution is extraterrestrial noise, and from about 1 gigahertz to 100 gigahertz, we have atmospheric noise as the dominant source for antenna noise temperature, right? Here in this square I put an example for the band to 1 to 10 gigahertz. The noise temperature of a night sky, it's in the order of 3 to 5 Kelvin, and the noise temperature of the ground is on the order of 100 Kelvin to 300 Kelvin. So if we have a directive antenna pointing at the sky or pointing at the ground, our antenna noise temperature can vary between these two values, right? So the directivity and the directivity pattern of the antenna also plays a role in the value of the antenna noise temperature. Now, so far we have been discussing about noise, and we've been dealing with one-port devices. What happens when we have two-port devices? Well, the concept of equivalent noise temperature can be very easily extended. And here I put the example of an amplifier having a power gain of G, right? And now, since equivalent noise temperature and power are proportional, I can write temperatures in noise temperature in this diagram. So if we have a noise temperature from the source of T sub S, here at the output of the amplifier, the output noise temperature will have two contributions, right? One would be the noise power coming from the input, which will be amplified by the gain of the amplifier, plus a certain noise added by the amplifier, because the amplifier is not ideal, it generates its own noise, right? So the definition of equivalent noise temperature for a two-port, for example, for a two-amplifier, is the noise temperature at the input that accounts for the additional noise generated at the output, right? So the definition of equivalent noise temperatures makes that this added temperature at the output is equal to the gain of the device multiplied by the equivalent noise temperature. The wording of this paragraph reproduces the wording of the definition of noise temperature given in the standard for the International Telecommunication Union, but essentially this standard says that the noise temperature is defined as the noise temperature of a two-port is defined by the temperature at the input that accounts for the noise added by the device at the output. There's an important case of two ports, which is lossy two ports. I mean attenuators or equivalent devices in which the attenuation is caused by dissipative loss. In those devices, there are thermodynamical arguments that justify that the output temperature there are thermodynamical arguments that justify that the equivalent temperature of this attenuator has to have this value shown in here in this slide. By the way, the convention in this slide is this attenuator, this L, is bigger than 1, meaning that if the attenuator is such that only 1/10 of the power at the input translates to the output, then L would be 10, right, and not 0.1. Now, in this case, the output temperature of the device is equal to whatever comes for the source divided by L plus some additional noise, right, given by this quantity. Now, there's a thermodynamical argument that gives you that this additional noise has to conform to this value. And the argument is that what follows. Imagine that here at the input we connect a resistor, a match resistor to this attenuator, and that assume that this resistor is at the temperature T. Now, for this case, the resistor would cause here at the output a noise temperature which would be T divided by L, right? On the other hand, the overall power of the noise at the output has to be also equal to T, because if it's otherwise, what would happen is that, if everything is in thermal equilibrium, there not be more noise power at the output than this. Or in other words, looking towards the input, if this is a match attenuator, we also see a resistor of temperature T, then therefore the output temperature has to be equal to T, right? And that justifies that the added noise by the device has to conform to this quantity here. And if you translate this quantity towards the input, it turns out that the equivalent temperature of an attenuator is L minus 1 multiplied by T, being T the physical temperature of the attenuator, right? Now, this is applicable to any type of match device whose loss is due to dissipation, right? For example, a transmission line, a waveguide, or an attenuator, right? The conditions are that it has to be matched and that the loss has to be due to dissipation. And this finishes this section of the lecture on fundamentals of noise.